years.
Okay. Good morning. I hope there's more of you online than there are in the room, and you're missing out on amazing coffee and some snacks here. So that's just too bad for you. This is the Corinne Clean Resource Innovation Network's Digital C3 Connect, Collaborate, and Conversation. So the idea was to get together, have some conversation around things. I hope you're having conversation outside this room. And today we're going to talk about what makes a good quantum computing project with a focus on the tailings ponds. So I'm going to let the speakers introduce themselves, but I would like to welcome Adam Ben Watts, Residence in Science with Quantum City, which is up at the university and is an initiative, I believe, of several universities across Canada. Quantum computing sparked my interest when I went to their conference a year ago, and we were there this year, and my husband shifted my portfolio of investments based on what we heard there. So pretty interesting from our perspective. And I'm really happy to bump into Abu Junaid again. He and I worked together at Total, trying to solve challenges in this space, and he's now with CNRL, and he's going to provide a real part of the real life story around how they tried to apply this or were successful. I'm waiting to hear with tailings. So welcome, and please introduce yourselves and enjoy the conversation.
Awesome. Yeah, thanks for the introduction. Yeah, I'm Adam, a scientist in residence at Quantum City, and part of the talk is going to be me explaining what that role is and what that job means. So we'll get the details. But well, yeah, I have an academic background. I studied quantum algorithms, was doing a postdoc on quantum algorithms at Waterloo before this position. And now I'm in this very fun position where I get to be at the interface of sort of academia and industry. So part of my job is looking what I think of inwards towards academia and bringing in quantum computing projects and thinking about quantum computing and how to apply it. And part of my job is reaching outwards to industry, to who maybe don't know things about quantum computing but are interested, and educating, but also learning from industry what problems they think are interesting, and being part of this sort of back and forth that I think is required to sort of bring new emerging tech to actual practical applications. So that's my background. What is this talk going to be like? I realized that, sort of this whole talk is just designed to set the stage for hopefully a nice Q&A afterwards. So this is really just going to be background on a few different things. So first, I'll give some background about Quantum City. I'll tell you, where I'm coming from, what I do, what we do. I'll try not to make it too much of an advertisement. It might sneak in a little bit, but I'll try and skim over that. And then I will talk about quantum computing and give you in just a few sentences, a couple of words, a sort of state of the industry, general questions about what I think is interesting, where we're going, what makes a good project at sort of this very high level. And then I'll pass it over to CNRL, who can talk, in more detail about the Tailings project and what they hope to get out of it, sort of what their motivations were, what they saw, and then we can have a proper Q&A and hopefully have an interesting discussion, which I'm looking forward to. But let me hop into it then. So, okay, what is Quantum City? What do we do? We are an institute within, we're part of the University of Calgary, but we are pan-provincial. So our mission statement is to really build the quantum ecosystem or help build the quantum ecosystem in Alberta. We're ecosystem builders. We've been around for about 2 years. And when we were founded, there was sort of this survey of Canada's quantum hubs, they're called. And what was noticed was that there are a lot of hubs that are sort of focused on lab to market, on sort of taking things from industry from academia, making startups, hoping some of them become unicorns, sort of pushing out that way. But there weren't a lot of hubs that were focused on reaching out to the non-quantum industry and sort of doing this, industry outreach, thinking about sort of market pull rather than push, So, and this is where we came in. So our goal, funded by University of Calgary, Government of Alberta, initially. Now we have some funding from the Canadian government as well. But our goal really is to start with the non-quantum industry, start with the real world problems that might benefit from quantum. And then to bring that information back, those projects back, that knowledge back to the industry and academia and what we call quantum solutions providers. So these sort of startups working in the quantum space. So that's, yeah, you can read the rest of it. That's in a few sentences who we are. Here's also who we are. Oh, yeah, good. So this is some of what I've said already. But yeah, how do we do this? How do we build this ecosystem? There's a few distinct pillars that are nice to think about. One is training, education, creating a pipeline. So we're focused on student training. In particular, we were part of helping set up at the university a professional master's. So this is designed it's a pipeline not into research, but to give enough quantum computing background to students that they can go out and join the workforce and be part of a quantum project. We also work on enabling infrastructure. I'll have one slide on that briefly. I'm an algorithms person, so I don't think too hard about the infrastructure. So it'll be a quick slide. But then we have this other sort of more nebulous one about narrowing the gap between quantum technology and solutions. And that's really where I come in. And that's part of, that's what this whole talk is going to be about. And that's sort of the goal of this whole talk, is to sort of bring these theoretical ideas that are on their way and coming one step closer to a practical solution. And that's, both our mission statement as an institution, and also very much what I think of as my role as being there in the institution. Oh. Okay, here's us. And this slide is, a few weeks old and it's already out of date. It's missing at least one new hire. But the reason I flash this and the reason I bring this up is because if you look at the job titles, we're mostly non-academic. I mean, I have an academic role, scientist in residence, but we also have inside the team a lot of experts in sort of business development, outreach, training. We're not a research institution. We are really focused on connecting with industry, connecting with business, and that's been a focus in the folks we've hired and the events we've done. And so we've got a really, I think, interesting and healthy mix of academic and industry expertise just internally in the team. Okay, I said I'd have one slide about infrastructure, so let me just say very briefly. In, I think, February 2025, we will be opening Q-Hub. And this is a space in the ARTC up near the university. But it's going to be a hub with space for us, the Quantum City offices, but also space for quantum startups, space for some folks from the university to come in, a collision space sort of around quantum. So on the sort of enabling our infrastructure side of things, that's what we're doing. We're also opening up a lab that will be open to both industry and academia. So this is a fab facility, clean room, lab. Again, I'm an algorithms person, so lots of those words don't mean a lot to me. But for people who they do mean a lot to, it's going to be a very exciting space. And I know there are faculty at the university that are excited about it. But again, our whole mission statement is also to connect with industry. So hopefully there is also industry partners who are interested in what's going on there and see some exciting possibilities surrounding having a clean room and a fab facility open to them. Okay, what else do we do? This is sort of exciting. Well, it's all exciting, but this one would have been a surprise to me before I started working at Quantum City. There's a Swiss venture capital investment firm focused on quantum called Chi Ventures. And they have partnered with Quantum City to launch their first North American office, actually their second ever office outside of their main one in Switzerland, here in Calgary. So they've got a cohort that will be, well, their cohort will be coming through, I think, starting in early 2025. And that's, yeah, they're great folks to work with. They've been around, but it's fueling the startup and the innovation ecosystem in one more way, right? There's great work happening at the university, but startups are another important way to bridge that work and academia. And that's another thing that's, part of Q-Hub, part of the sort of quantum ecosystem that we're trying to build. So yeah, what is your quantum computer? It's a box that processes classical input to classical output, that we understand, but through a different sort of set of operations. So, at the hardware level, which everyone in the room knows, but people online, I think at the hardware level, your quantum computer is different. It's the basic operations that are being implemented are a richer class of operations than just sort of the binary yes/no decisions that computers make. We have this idea in our mind one day of having a computer which is the ideal standard of quantum computer is one that's universal, which means that the set of operations that you can implement are rich, are full. You can implement every operation that quantum physics allows you to implement, your quantum computer can implement. It's large, meaning that you can handle a large set of inputs and create a large set of outputs. And it's fault tolerant, which just means, again, this is funny for us who are very steeped in the classical world where things just work the way we want them to. We take for granted that our computers do what we want them to. But fault tolerant means that the operations that your computer actually implements are the ones that you tell it to, that you don't have errors through your computation. This is the ideal sort of quantum computer. The ones that we have today are not this, so they're limited. They're shallow, meaning the amount of time that you can process information for is limited. The sort of set of algorithms that you can implement are limited. The amount of processing available to you has some limitations. They're of limited size as well. So not just the computation time, but also the width, the number of ones and zeros that you process are limited. So you talk about the number of qubits that your machine has on it. And state of the art for sort of universal quantum computers is about 150 qubits. So that's 150 zeros and ones that you're mapping through this procedure. And they're noisy. So this is the opposite of fault tolerant. This means that the operations that do get implemented on your quantum computer might not be the ideal ones. So you have to just accept that sometimes your quantum computer won't do what you want it to do. And this, again, limits the sort of complexity of algorithms that you can implement. Algorithms that are, it's the algorithms that are more delicate, algorithms that can't handle an error in their execution break or just are infeasible on today's quantum computers. So the only ones we can implement are algorithms that are a little more robust to errors, that can accept a few mistakes along the way. But the excitement, the reason that it's now is a good time to start projects is that even these limited machines still seem capable of processing information in a way that isn't possible classically, or is very hard to do classically. So even though you have all these restrictions on the sorts of input-output mappings that you can perform, it does still seem like these machines can perform input-output mappings that classical computers cannot. So this is a promise that says there's some potential here. There's some sort of super classical capabilities that these machines have. And the question is, what is this useful for? Is this useful? How close is this to being useful? And that's sort of the questions that guide quantum computing projects. Okay. And now I'm just going to sort of say interpret what I've just said sort of now with a bit more of an industry lens. And say that, the potential of these machines comes from the fact that you can hopefully, the potential applications of these machines cross a lot of different industry verticals. So these sort of eventual machines that we have in the future, these fault-tolerant machines, we think sort of a killer app that we expect to use them for is simulating nature, simulating quantum physics. And this has sort of a few immediate applications across a few different industry verticals. So there's applications in energy, sort of material science. There's also applications in drug discovery, pharmaceuticals. When you don't think about this sort of a universal fault-tolerant machine, the machines that we have today and the universal ones also seem like they'll have the capability to solve optimization problems. Here you're really looking for problems where the quality of the solution really matters. Hard optimization problems where you're getting an approximate solution and getting a slightly better quality solution seems like it would have a significant advantage. There's reason to invest in getting a better, tighter solution. So finance is sort of a natural application of that idea, right? Where your quality of solution really, really matters. Logistics as well, where you're solving some hard transport problem and doing 3% better would mean a big change for your costs. Yeah, I'll just mention it. I didn't say it before. There's also this, if you look at quantum computers, you hear a lot about them breaking encryption, about them solving factoring. This is another capability of these sort of universal large fault tolerant machines. This is another killer app in that, it's hard to do classically. Unfortunately, the biggest advantage we see to it is breaking encryption schemes, which is sort of a negative one, right? But it is exciting from the point of view of you're solving a problem that would be hard or impossible to solve on a regular classical machine. But again, that's a capability we don't have until we have universal large fault tolerant machines. Okay, what are the challenges? And I think we're syncing up back to the live talk now. So what are the challenges? The biggest one is that the machines that we have today are limited. You're unlikely to see performance out of your machine that really changes your bottom line, that really affects operations even. Now we think these changes are coming. We think these machines are getting better, but the quantum tech right now is still very much in the R&D stage, where the reason to do a quantum project right now is to start preparing for quantum computers when they come along, to start understanding what sort of problems make sense on quantum computers, to sort of benchmark what current capabilities look like, so that you can understand the development of quantum computers. But it's not a packaged product ready with promises that it'll solve your optimization problems with a 5% better quality or something like that. I mean, and you shouldn't go into a quantum computing project expecting that even. So limited short-term applications. It's complex. You need some amount of quantum, and the whole field is getting better at making quantum more accessible, making onboarding easier. But it's still at the point where, to do a quantum computing project right now, you need to take the lid off a little bit and look at the bits and pieces and look at the sort of, code again, perhaps down to the gate level, down to the individual operation level, and sort of troubleshoot. And, because these machines are so limited, a quantum computing project right now really requires you to get as much as you possibly can out of them to start to see an advantage. And this needs some amount of expertise, honestly, with people who even know the hardware, so not just an algorithms person like myself, but also someone who's worked on the quantum computer, understands the noise, can tell you that projects don't work well on a Tuesday because there's a train passing by and that, disturbs the machine. I mean, that's the level of sensitivity that we're dealing with here. And I'll put another challenge or risk that has a different flavor, which is that, right now we're in a stage where we're not seeing a lot of commercially viable uses of quantum computers, because the computers are getting better, they're limited. Sort of the moment we do, the whole stage might flip, and I'd compare this to, say, AI right now, where to do cutting edge AI research now, you has such resource requirements that, the amount of compute you need, the amount of GPUs you need, even academia has trouble doing cutting edge AI research now because industry, because of the costs associated are so high. So, there aren't that many quantum computers in the world. And if they start to be very useful in industry, getting time on them is going to be very hard. So that's, that's not a problem we have today, but that is a way that the field could evolve. Okay, what are the benefits? What are the reasons for doing a quantum computing project? And I sort of said these before, but I just want to make it clear, why should you do it? Well, one very nice thing about a quantum computing project is it's a good way to understand the technology. It's a good way to understand the technology. I mean, selfishly, I really like doing projects with industry because I get a problem that someone really understands and really cares about. And then when the quantum computer gives me a solution, I can talk to somebody who says, this solution is good, this solution is bad. It makes a lot more tangible for both quantum researchers and I hope for industry, sort of what these computers are capable of. There are lots of studies benchmarking the performance of quantum computing on sort of a range of optimization problems. These are nice, but they're inconclusive. Again, there's not this like shining star, but to take a real industry problem, to take a real problem that you care about and see the performance on a quantum computer on it, I think makes it all a lot more meaningful and gives you sort of an understanding of, okay, if I had 500 qubits instead of 100, would that matter? Would that now make this thing useful? So that's, I think, honestly, the biggest benefit. You also sort of get to revisit hard problems, change your approaches. Just the process of implementing a problem on a quantum computer sort of requires you to rethink it a little bit. And there's a lot of sort of quantum-inspired approaches that come from this process, where you take a problem, you run it on a quantum computer, and just the process of changing the problem gives you a new algorithm, even a new classical algorithm for solving your hard problem. So there's a benefit there. It lets you build a relationship with a quantum solution provider. And this gets back to that other point of, once these machines become commercially viable, there's going to be long lines to get time on them. And I genuinely think, I mean, certainly in my role at Quantum City, but also in industry, if you're planning on using a quantum computer eventually, now is a great time to get to know the people building quantum computers. Now is a good time to build that relationship. And you get to be involved in sort of co-development of new quantum algorithms. The field is still exploring, it's still looking for algorithms, looking for opportunities. The projects that get implemented now sort of have an outsized pull on a lot of researchers' time and effort and energy. And so, now is a great time to steer the field as a whole and what it thinks about and where the first new algorithms get developed. So that's another, advantage to a quantum computing project right now. And then, of course, eventually, the excitement is that you have a project and time on a machine, and you're solving a problem that you couldn't solve any other way. But I put the word eventually there, and it's important. That's not the promise right now, but that's of course the whole driving idea behind the field. And it is real. It is coming. 2030 is a date that I keep saying, but back and forth with industry. Anyways, yeah, that's okay. That's it for me and my background. And now I have some other slides here about the Tailings project and the specific project we do with CNRL, but I think it makes more sense for you to hear from industry at this point than me. So I will pass it off, but hang out in the audience.
All right. Good morning, everyone. My name is Junaid, and a little bit background about myself. I'm a technology and innovations project engineer at the Canadian Natural. My background is by background, I'm a chemical engineering scientist. I've been working in this industry for about 14, 15 years now. Interestingly, the person who hired me in my first job in the industry is in the audience right now, Heather Herring, and at Total Energy back in 2010, 2011, around that time frame. Anyway, I mostly worked as a technology development engineer or an R&D engineer in Total, Shell, and now in Canadian Natural. Mostly worked in extraction and environmental related problems in the oil sands industry. So, sorry about that. Like, I think I was pressing probably the wrong button. Anyway, so to chat about, I know very little about quantum computing, so my apologies for that. I definitely won't be able to talk on that particular topic. But what I can talk about is the challenges that we are facing and why we think quantum computing can provide us a solution to our problems. So about the challenge structure, the specific challenge that we are going to talk about, like it's basically this is how it is structured. The organizer is, of course, Quantum City at University of Calgary. And then the computational power capacities, including servers, are provided by the Amazon Quantum Solutions Labs. And for the challenges we are currently dealing with now, the corporate partners are ATCO Space Labs and Canadian Natural or ourselves. So currently there are three challenge tracks. So one is on smart charging. That's basically with smart ATCO Space Labs. And the other two, those are energy-related challenges, are with Canadian Natural. One is on bitumen viscosity, but the one that we are going to talk about today is the tailings treatment. So the incentives for the challenges are, there's a small cash incentive. It's not huge. It's a $10,000 Canadian. But I think the bigger driver here is the opportunities to speak about the issue and how quantum computing is addressing those challenges at the innovation conferences, Q Connect and Inventures, as well as follow-up opportunities with the partners. So essentially, if this shows potential, and there are a lot of other problems that we could probably leverage on quantum computing in terms of solving those. So the specific challenge that we are going to talk about today is the tailings treatment. So those who are not very familiar with oil sands operations, it's not conventional oil. Like it's not stored in an underground reservoir or underground. It's a mixture of oil and sand. So it's just basically the bitumen with very heavy oil fraction is mixed together with the sand matrix. There are different ways of extracting the bitumen or the oil from the sand, and one is in situ or thermal operations, but the majority of it, like the majority of the operations are mining based. That's the massive scale operation. So what we do is we mine the entire mixture, and then we use a hot water in a hot water extraction process with some chemical additives to extract the bitumen from the sand matrix. So as a byproduct after extraction, what remains is a mixture of solids in water. Now, the solids in water, there are different fractions. So obviously the coarse sands, it's easy to settle. It is in a sand mixture, is huge. It settles down pretty easily. But also there is a fines and clay mixture, and those are very difficult to settle, especially the clay particles, which have electrostatic double layers of negative charges. They repel each other, and so they're very difficult to agglomerate and settle. Currently, I think the numbers vary between operations of different operators, but we use roughly from 0.5 to 2 barrels of water to produce a single barrel of bitumen. So you can understand the volume, the massive volume of water that we have to deal with. And following processing, it ends up being this huge slurry or mixture of sands, fines, clays, and water stored in a huge pond. So why do we need quantum computing to solve this? So it's a decades old problem. All the oil sands operators had been trying to address it in different ways for a long period of time. I guess like the very short answer of it is like I think we do not still know fundamentally like what the issue is. It is a very complex system, and I boiled it down to very a simplistic way, but boiled it down to in a very simple way. But you have bitumen, which is a very sticky particle of complex organic composition. A little bit of that still remains in the tailings. And then you have these clay particles, clays of all various sorts of structures with, electrostatic charges. There's water chemistry, so the pH level, it might vary depending on your process conditions and so on. So at a very fundamental level, it is really difficult to understand, what is preventing those particles to actually agglomerate and settle down. People have tried different ways of treatment, like polymerization or adding a coagulant to neutralize the charges, and then adding a polymer to, form agglomerates and then settle. Mechanical ways of settling, all different kinds of things. And the main issue here is like what works for some do not work for others. does not work for others, right? And so it's kind of gotten into a trial and error and an empirical kind of solution for each operator. And even among each operator, it varies between the different assets just because the ore properties and the system is so different between the different assets. So what we want to get out of this challenge is try to understand. We want to understand what the barriers are and what can be done fundamentally to solve this, rather than trying out in a trial and error method and coming up with solutions that probably is not universal. Why is it big? It's obviously a real world problem. It's just not made up. It's not an academic exercise. Um, just to give you an extent of how big this is, like the tailings ponds are massive, right? Like this is probably the only man-made water structure that I can actually see from space. Let's put it this way. I mean, it's probably not environmentally very harmful because it is a mixture of water and clays, but we have a mandate to reclaim the land and to bring it to its original state following completion of our operations. So this is a $1 billion liability, and we need to find solutions that is sustainable and effective. And this is why we had been investing a lot of effort and funding in trying to come up with solutions for tailings issues. So I think it's probably a good idea to again hand it over back to Adam, because he's probably more aware of of the specific responses that we received to this challenge. But I'll just end up saying we did receive a couple of proposals, and then we did select Accenture for Accenture's quantum team to resolve this challenge. We are absolutely delighted and happy to be a partner, and I'm proud to be a partner of this initiative. And I thank you for inviting me. I'll be happy to address any questions you might have on it later on. So with that, I'd like to hand it over back to Adam.
And I can do this fast because I think I've just got a few bullet points, and then most of it can come out of the Q&A anyways. I think I'm just going to fill the rest of this slide. But yeah, let me say just a tiny bit about what Accenture did. So yeah, I said everything I said about sort of the limitations of quantum computers, how they're limited in capability at the moment. And I think Accenture took what is a very wise approach, which is they started by saying, okay, what's the best classical solution to this problem? If I didn't have a quantum computer, what would I do? What seems interesting? And they took a sort of neural net approach, quantum machine learning approach to, I think, now I'm going to say some words and you're going to tell me if I got them right, but I think they're in particular, yeah, they were predicting how flocculants would affect the settling rate. And there's a goal to sort of generalize from this, or an idea that you could generalize this from mixtures of flocculants and coagulants. But what they did is they took this classical solution, this classical machine learning neural net solution, and if you have a neural net background, they changed a few of their nodes, a few of their neurons to be quantum. So they had basically a quantum processing layer that fed into a classical layer. And the idea, this is not an approach they invented. It's been out there. The idea is sort of that you get your classical neural net, but you get the benefits of some of this quantum processing in there, right? You get this this layer that can't be simulated classically, that especially if your problem has some quantum or some sort of quantum physics levels, you hope that this, well, yeah, it's trainable, and you hope that there's sort of an extra layer of expressivity that you get out of your quantum layer that you wouldn't have classically, that then gives you a better quality solution. It was small, the solution that they submitted. We knew this going into the challenge. Again, partly because time on these machines is expensive, partly because it was a year ago and state of the art then wasn't even what it is now. So I think they simulated something like 15 zeros and ones. That's it. So this quantum layer. But what they showed is that there's a lot of sort of classical understanding the literature, surveying the scene that went on. But what they also showed is they tried very hard to compare this small quantum network to an equally small classical network, and say that, you know, if we compare sort of apples to apples in terms of size, we see more expressivity coming out of the quantum network than the classical network. And this was, you know, they pitched it, and we sort of received it as a positive signal, right? As an idea that there is an advantage, at least, that's worth investigating here. There's a reason for follow-up work. There's a reason to keep up to date. So yeah, that's the sort of nitty-gritty of the solution. I can say more about it, but I think if that, hopefully that gives you a flavor of sort of where quantum is at, where it's going, what we're looking for, what sort of these projects have to do. I will say that, yeah, already computers have come a long way in hardware from what Accenture had access to do this project a year ago. So, you know, already this becomes something that would be interesting to revisit. And again, if the development timeline comes the way that the roadmaps say it will, in a couple of years, it's going to be even more exciting. Okay, but I think that's it. Let me just make sure. Yeah. So thanks, and we can do Q&A now. Happy to chat about all of this. Yeah. Oh. Sorry,
Great presentation, Adam.
Thanks.
Thank you. And great to hear the industry perspective as well. So earlier in the presentation, it was suggested that one of the outcomes from this type of research is an understanding of something that can be applied in the classical world. Or maybe this has shown, so my question goes to what was the tangible takeaway from this work? Was it more knowledge that can be applied in the classical world, or a better understanding of the problem, or a better understanding of how to solve the problem with quantum computing?
Yeah. Okay. I could try and answer, but maybe it's better that you'll get a more honest answer if you answer, right? So sure. Yeah, we can. Here, should we? Yeah, sure. Make this a two-person panel.
Thank you. Yeah, thanks, Ed. It's a very good question. I think it's a bit of everything that you said, right? Like, so obviously, like, you know, understanding what the problem is, well, it will lead us to a potential solution, right? So first of all, understanding the problem fundamentally, and then probably finding out why some things are working and some things are not working, and eventually leading to a better, you know, robust, sustainable solution. So I'll give you an example of there. I probably mentioned in my talk, like, you know, we use different kinds of coagulants or flocculants that to neutralize those charges and then do agglomeration and so on. And it happens like, you know, some of them work in some certain setup and some of them don't work in another setup. So what classically, it had been very, very difficult to model that in classical computing. We simply didn't have the ability or computational power to simulate that environment and simulate that environment and understand. So this is where, you know, we are trying to you know, get answers from quantum computing with this new computational ability, like, you know, if this is the structure of these certain chemistries of certain materials and tailings, how are they going to interact? Whether they're actually helping in you know, neutralizing the charge, and if not, then why not? And if a certain chemical is not working, then which chemical can work? And it potentially leads to, you know, even developing a completely new set of chemistries that'll be way more effective in doing tailings problems. I don't know if that's the kind of answer you were looking for, but
I'll put you on the spot if that's okay, and ask. Yeah, I think I got a partial answer to this from JP once, but had CNRL looked at sort of ML approaches to this problem before the challenge, or, you know, was there because, you know, that's part of what came out of this challenge, right? Was this proposed ML approach with a quantum layer, but also just a proposed classical ML approach. So
I I do not think CNRL as a company has had this approach, like I said, but it's a decades, right? Multi-decade problem that existed within the industry. And I'm aware of, some of the classical approaches undertaken by other companies, especially Syncrude and probably some at Shell too earlier. But Shell is part of CNRL, so I know take what you want to get out of it. But I don't think CNRL, itself had undertaken it, but you look at all the initiatives within the tailings world now, like under the Canadian Oil Sands Innovation Alliance or COSIA, pretty much every environmental concern is addressed collectively by the industry, and so it's a consortium of all the oil sands operators. So whatever research is done by one company is passed on and shared with the others, so we can learn and implement. It's a joint effort. So through that, we have access to some of this older work that had been done by other companies.
I could say more, but we can just do another question too. I mean,
So what does the output look like?
from a quantum computer, at some level, it's a bunch of zeros and ones. I mean, these machines, classical input, sort of quantum process, but when you take off the lid and measure, you're just getting zeros and ones. Because these machines are so noisy, really what you're looking at is more a distribution. So you're sort of shaping probability distributions is sort of the level. So for optimization problems, for example, you're looking at a distribution over possible solutions, and you're hoping you find a good solution inside that distribution.
Okay, so you'd apply that then, say, for example, to different charges in water chemistry, or you would have a range of different water chemistries and then apply the different outputs to that as a kind of calibration.
Yes. Yeah, and I mean, we're approaching the level where you could have an actual description of a physical system that you get out. I mean, your system is very small and very simple. You can do it already. I mean, you can do it by hand on a piece of paper, but we're approaching the point where there's sort of interesting chemistry that you can talk about with this. So a description of the ground state of some physical system. Again, sort of distribution over energy levels that means something. But this is sort of where we're going to. I think for this particular project, because it was the first layer in this neural net, the output wasn't even meant to be interpretable, sort of human interpretable yet. It was the input was some description of flocculent concentrations and system. The first layer of the neural net was quantum, but then it got passed to a few classical layers of neural net that then at the end was going to give you a prediction about settling rates.
We have a question online. How would quantum compute overcome the typical limitations with classical computing, where the quantity and quality of data available to train the algorithm determines the accuracy of the predictive capabilities you get?
Yeah, great question. Also, props for whoever stated online. Thanks for sticking with it online. Yeah, okay, that is a great question. Quantum computers are not magic. So, there are information theoretic limitations on the sort of inferences that you can make from data that are still true. If you don't have a good enough data to make the proper inferences, your quantum computer isn't going to help with that problem. Where we expect or we hope to see an advantage for quantum computers are in things like model size and perhaps training time. So, expressivity, these sorts of things. If the correlations are sort of complex, but if there are correlations that your classical model, we hope that if there are correlations in the data that you're given that your classical model cannot capture, maybe your quantum model can. That's the idea. So it's if your fundamental restriction comes from data quality, your quantum computer probably isn't going to help. if your data is very high dimensional and you're not extracting the right correlations with your classical model, because it's small and because to get the correlations would need some gigantic classical model, maybe a reasonably sized quantum model can do something. That's that's the area of active research. I'm not gonna, there's sort of question marks around this whole QML approach. Because, even classically, it's very hard to prove what ML can do. You just run it and see and experiment. Same quantum leap, and the machines are very limited. So early days for the field, but that's the idea.
Okay, so I just have one last question, and it's really actually carrying on from that, what you just said, related to data input, or I guess the modeling that you input you start with. How easy is it to modify if you discover that your assumptions are a little off, or your model is a bit off?
Yeah. It's probably one of the honest answers is so the reason I'm hesitating is because it's easy these days because the quantum models are small. The whole, because the size of the quantum computer is so small, things like training, updates, modification is all pretty fast because we're still, sort of barely stepping outside of the toy model sort of era. Now, I think there are a lot of questions sorry, I've changed your question a little bit because I started thinking about training, which is a slightly different question. But certainly training large quantum models still has some questions around it that we don't have an answer to yet. And I think we just need to have the models to play with to see what happens. Similarly, tweaking the model, adjusting the model. I think we have ideas, but I mean, changing your classical data isn't too bad. But if you ask me if I change these parameters, does the model still perform well? I have no idea. And a lot of that just requires, I think, trial and error with the actual models to answer.
So minor modification to that online, due to the changes in computing ability, is there a risk that information we get today could be different from what we get in the future?
Okay, let me.
So maybe the outputs?
Yeah. Yeah, I'm trying to. It's a good question. I'm just trying to walk in the right answer. Yeah, there's certainly, if you're getting the right answer today, then hopefully the quantum computer still gives you the right answer. You're solving the problem. If your classical techniques are solving the problem, that's not going to change. Now, when you're not solving the problem classically, when you're missing, when you're approximating, when you have a solution that you think is good enough, but you don't think is necessarily optimal, yeah, there's a chance, risk, excitement, that your quantum computer will give you something that your classical computer isn't. That that you'll find, get one step closer to, say, ground truth. Okay, and this is the question said risk, so I'm gonna tweak it a little bit and say now that there is also a chance that the whole sort of workflow has to change when you have a quantum computer as opposed to a classical computer. These sort of machine learning models are nice because you can sort of understand it, say change it a few of your nodes from classical nodes to quantum nodes. That doesn't sound like too dramatic of a change. But because quantum computers are limited in size right now, sort of the way you break up your problem, the way you process it, looks a little different quantumly than classically. So there's, I guess, a risk there in terms of how you think about problems and how you process them, that there's certainly some overhead that you have to do in transitioning to quantum.
Okay. Thank you, Adam and Quantum City, Junaid and CNRL, Heather, the digital theme from Crin, everybody who joined us online today and actually came back after all of our technical challenges. We're so sorry about those, but the recording will be uploaded and will be available if folks didn't manage to make it back. Thank you to everybody in the room. We are happy to have you, and please stay and enjoy some networking and have a great day. Thanks.
I'll just add, partly for the recording, you know, if you have questions, please feel free and email me. I'm sure my email will be somewhere. You can Adam Quantum City will find me, Adam Betty Watts. But yeah, happy to take questions after this for anyone. Yeah.